Okay, ladies and gentlemen, so the last set of notes for the periodicity unit is all about reactivity, okay? So the trends in reactivity. Now, generally, when we're talking about reactivity, what we're talking about is the speed with which things occur. So we're just going to define reactivity for our purposes. We're going to say that reactivity is the speed with which a reaction occurs. So the faster the reaction happens, the more reactive the atoms or molecules that take place or that participate in the reaction are. All right, so, whoops, let's try that one more time. All right, now, the example that I'm going to give for this particular thing is going to be the reaction of sodium with chlorine. Okay? And so that's the one that I'm going to use. So for our example, we're going to be using sodium and chlorine. Now we need to kind of put it all in perspective and decide what it is that we're working with, okay? And also use this as a chance to review the periodic table. So we find sodium on the periodic table. Sodium is over here, right? This is the dividing line between the metals and the nonmetals. So sodium is a metal that is in group 1, right? So sodium is in group 1, and group 1 is a member, or is a family called the alkali metals. Okay, well, I'm going to switch over to green for the other. Chlorine is here. It's on the right side of the stair-step line. So chlorine is a nonmetal. And that's a nonmetal from a family called the halogens. Okay, so that's a nonmetal. And that is in group 7. And as long as I'm going to stick with green, I might as well just stick with green the whole way. So that's chlorine. All right, now let's take a look at what happens when we react sodium and chlorine together. Now I'm going to simplify this just a little bit, and you'll find out later that what I'm saying today is not strictly speaking exactly all the way correct, but it's definitely going to give you the idea. Okay, so apologies for when you find out later that a little bit of this is slightly misleading, but I do it for a good reason. And we're going to make sodium chloride, which you in your sort of everyday life call salt, right? That's the salt like you would put on French fries or whatever. All right, so here we go. Sodium, if we look at it in the periodic table, has got 11 protons, so we have a positive 11 in the nucleus. That means it has 11 electrons when it's neutral, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, now chlorine, on the other hand, has got 17 protons, plus 17, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And actually, just for the purposes of making this easy, and you'll see why here in just a second, I'm going to put that electron right there. All right, now, what's happening is this, okay? We'll find out later when we do reactions that every element is trying to get what we call a noble gas configuration. It's trying to get 8 electrons in its outside shell. So we're trying to get that noble gas configuration. Noble gas configuration generally means 8 electrons in the valence shell. If you look, chlorine is almost there. It's got 2, 4, 6, 7. Sodium's a long way away, but here's the thing. If it loses that one right there, then it has 2, 4, 6, 8 in the next shell. So all chlorine needs to do is to take this electron and give it away to that one. All right? So that's basically what it does. So this electron right here is pulled away from the sodium atom. Okay? The energy required to do that is called the ionization energy. If you recall. And the ionization energy for chlorine, or excuse me, for sodium is 498, 5.8. All right, now, chlorine wants to accept the electron. It is attracting the electron. And if you recall, the thing that we measure for the ability to attract an electron is electronegativity. So the ability to attract this electron is called electronegativity, and for chlorine, that electronegativity is 3.16. All right, as long as I'm going to do green, I might as well just stick with green. All right, 3.16. So basically what happens is this electron right here is removed from sodium and given to chlorine. Now, when that happens, the sodium has now lost an electron, gives it a positive charge. And so sodium has now been turned into a cation. The chlorine has gained an electron and it now has a negative charge. And chlorine has been turned into an anion. Now, the question about reactivity is, what is the trend in reactivity down the alkali metals? Well, you can see that ionization energy is the thing that governs the reaction. The lower the ionization energy, the faster the reaction will occur. Well, we discovered in our atomic guided notes section that the reactivity, the ionization energy decreases down the group. So the ionization energy decreases down the group. Make sure I keep my colors correct. And so the most reactive one is going to be the one with the lowest ionization energy. So potassium is going to be the most reactive. And lithium will be the least. So reactivity increases down the group. For metals, reactivity increases down group. Down the group. Well, the ability to attract that electron for nonmetals is what counts. And so for those guys, it's the electronegativity. The bigger it is, the better it is, because it attracts the electrons more. Well, if we look at our periodic trends guided notes, we see that electronegativity also decreases down the group. Or if you want to think of it this way, the electronegativity increases up the group, right? And so our most reactive nonmetal is going to be the one with the the highest electronegativity, and that is fluorine. Most reactive. And so the electronegativity, highest towards the top, most reactive. And so for the nonmetals, the reactivity increases up the group. So, in summary, what makes a metal reactive is a low ionization energy. Okay? That's what makes metals reactive. Lower you go, more reactive they get. What makes nonmetals reactive is a high electronegativity. The higher you go, the more reactive they get. And so the most reactive pairing, of course, would be potassium reacting with chlorine, and the least reactive pairing would be lithium reacting with iodine.